Okay. Let me get this to where it's only on half my screen so that I've got a work thing. So what you want to do with these kind of problems is take one thing at a time. In other words, do all your numbers first, then do the x variable next, and then do the y variable, and if there's more variables, then do them after that. All right. One at a time. So, what are the numbers part?
36 and 4.
Well, what's 36 divided by 4?
Is it 9?
Okay.
No, 8.
So I've got a 9, and I'm going to put a fraction bar there, just in case we need it.
All right.
Let me think about that for a moment, whether that's the best way to do it or not. You know what? I'm going to leave that fraction bar out, just as a way of understanding how to do this. What is x squared divided by x? The next thing you run into are x's. So what does that equal to?
That is just 2x.
No, what you do is you subtract the exponents. So what's that equal to?
X.
So that x goes there, and always know that if there's no exponent, it is a 1 that is indicated. And finally, the y. What is y to the third divided by y to the fifth? What's this?
Is that y squared?
It's y to the minus 2. Right? You see why? 3 minus 5?
Yeah.
Okay. However, what they usually want on these things is your answers with all positive exponents.
Yeah.
So we need to get that y on the other side of the fraction bar. So my 9 and my x are in the numerator because they have positive exponents. But the y is in the denominator. In other words, whenever you see a negative exponent, put it on the other side of the fraction bar and change the negative to a positive.
All right.
In other words, even if you have something like this, 1 over y to the minus 3. Well, I can just put that thing on the numerator side with a positive 3.
Yeah.
And then, of course, the 1 is presumed. But that's the way you're going to handle negative exponents. Now, I could have dealt with this problem and gone directly to this, but these formulas for handling exponents are pretty important to memorize. If you're dividing, you're subtracting exponents. If you're multiplying, what's x cubed times x to the fourth equal to?
Is that x to the 7th?
Yeah, because I am multiplying the underlying base, so I'm adding the exponents.
All right.
So when you're dividing, you're subtracting. When you're multiplying, you're adding. All right. Let's take a look at the next one. Let me go ahead and write it out. For some reason, I feel more comfortable when I have it written on my thing. Now, okay, the parentheses are needed. What's the first thing we want to do here?
Does it give you exponents?
Not the exponents, the top exponent. This one right here, we want to apply that. It's kind of like distributing it. So what we want to operate on that right there. What is that answer? And is all you need to do is apply to the upper 2 to each variable. Apply it to the 2, apply it to the x squared, apply it to the y cubed. So what is it?
Is it 4x power 4?
Here you multiply the exponents.
Yeah.
In other words, I have a tendency to call this double exponentiation. Okay? Where I've got a small exponent and then the whole thing is being taken to another exponent. That's why I call it double exponentiation. Well, when you're doing double exponentiation, you multiply exponents. So that becomes x to the 4th. And what's the y thing become?
Y to the 6.
Okay. Now, I don't need this parentheses anymore, but I'm going to put it just for clarification. And in fact, I don't need either set of parentheses. I could erase them and the meaning is the same. Let's do it. And the meaning is that everything you see is being multiplied.
Yeah.
Okay, well, let's multiply the numbers. What do we get? Let's multiply the x's. What do we get?
X to the power 5.
And multiply the y's.
Y to the 10th power.
To the 10th. And sometimes I'll cross them out just if it's a really complicated thing, just so I don't get lost and forget to do one of the variables or something. All right, let's go on. Hold on, let me. Okay, so here we have depreciation.
Yeah.
Using the function, the value of the car, which I'm going to call f of t, at the end of some number of years, is equal to its starting value, a, times 1, and since it's depreciating, it's minus r. If it was appreciating, it would be plus r. T is the number of years.
Yeah.
So fill in everything. So the future value of the truck, I guess it's a car, okay, equals what? What's A?
What is what? A?
What is A?
You want me to list the transformations?
I want you to plug in, it's not a transformation problem. It's a compounding interest on either appreciation or depreciation. And so A is the starting value. What was the car originally worth?
It was originally worth 15,000.
That's what A is.
Yeah.
What's R?
R is yeah, not what R would be.
Read the second sentence. If his car depreciates 5% per year, that's what R is 5%. Yeah. Okay? Now, you never use percentages in equations, or at least I don't. So I'm converting that to a decimal. So that's 5% is the same as 0.05. T is what?
T is
6 years. Now, t is not always in years. Sometimes t is in months, sometimes t is in days. T is always in the same unit that the R is in. They told us R was 5% per year. That means t is in years. If they'd have said if it's, bacteria growing as 5% per day, then t is in days. But the units on t are always the same as the units on the rate. Okay, so this is just a relatively straightforward problem. You have to do this in your calculator. I'm going to combine the 1 and the minus 0.5 to get my 0.95. So in your calculator, take 0.95 to the 6th power and multiply it by 15,000. What do you get?
Multiply that by 15,000?
Yeah, that's what that equation says. Just take 0.95 to the 6th power. You're not taking 15,000 to the 6th power. That 6 only applies to what's in the parentheses below it.
So
you're going to get a number less than 15,000, considerably less. What do you get when you take 0.95 to the 6th power?
I get 34.2.
34.2?
Oh, but I think I did this wrong.
You're doing it wrong. It's, first of all, when you take numbers that are less than 1 to powers, they get smaller. They don't get bigger. They get smaller. They never get bigger than 1. Okay, so when we take 0.95 on your calculator, what you're doing is taking 0.95 and then use that arrow thing to the 6th. That's the way you take a number to the 6th power.
The arrow thing?
Yeah, this arrow thing right here. There's a key on your calculator that looks like that arrow.
I think I got it. You
think you got it?
Yeah.
Okay. What do you get when you take that number to the 6th power?
0.735.
Okay. Now multiply that by 15,000.
You get 11,026.
26?
Yeah, 11,026.
That's what your car's worth after 6 years. And that's pretty realistic. In fact, 5% is pretty small. Most cars are going to depreciate. Gosh, when I was growing up, my dad told me you walked out a new car out of the dealership and it would depreciate 1/3 per year. That's like 33% per year. But they build cars better now than they used to, so cars don't depreciate as fast. The age of a car isn't perhaps as important as it used to be, although 5% still seems a little low to me. But anyway, that's the way you figure it out. In other words, you start with the function they gave you, and you have to know what everything is in this. There's this variable, there's this variable, there's that variable, and there's that variable. If you don't know what each one of those means, you can't do the problem. So you have to know that A is the original value, R is the rate, and T is the number of years. And F of T is the future value of the car.
Yeah.
All right. Let's go on to the next one. So we're looking at is this arithmetic or geometric series?
Geometric.
They don't really need the parentheses around the R. although I don't blame them for putting it there. The R is such a key number here.
Yeah.
Okay, if we look, given the following table, write the geometric sequence, and the table is the first term is 5, the second term is 25, the third term is 125, the fourth term is 625. Now, what I wrote at the top of the page is the general formula for all geometric sequences. What they want from you is the exact formula for this geometric sequence. So you're still going to have an a sub n, but they've given you a sub 1. What is it? It's the first term. First term is right there, 5. That's the first term, that's the second term, that's the third term, that's the fourth term. That's what their table means. The 1, 2, 3, 4 across the top means that's the nth, first term, second term, third term, fourth term. Okay, so a sub 1 means the first term. In this case, it's 5. What is the common ratio or multiplier between every term? Okay. And then this is always still n minus 1. In other words, this is the answer they want. Okay. And notice that with this answer, if I wanted to know the 35th term, I don't have to multiply that by 5 35 times in a row to come up with the answer. I can use this formula. It's 5 times 5 to the 34th power. You can put that in your calculator and come up with it in about 10 seconds.
5 times 5 to the 34th power?
What's that?
Wait, you want me to give you 5 times 5 to the 34th
No,
power?
I don't want you to do that. I was just, they don't ask for any more than this equation.
All right.
I was just extending the concept a little bit. The reason this is a key equation here is that it will allow you to figure out whatever term you want. If you wanted the 1000th term, you could get it from this equation. That would be a sub 1000. In other words, n is 1000, and that's going to be 5 times 5 to the 1000 minus 1, which is 999. So there's the 1000th term of that sequence. That's the reason we care about what the nth term formula or equation is. That's the specific nth term equation for this sequence. All right, let's see. Let's look at the next one. Which is linear and which is exponential? Okay, if I'm not sure what the A and the B are at the bottom.
Yeah, that one's constant.
But there's 3 rows here that they're talking about.
Yeah.
And this row goes 3, 12, 48. The heck? Something is, you know, I wonder if that's the fact that I've got it too narrow. Here, let me, why is that 2 out of place? Is that supposed to be 192? Yes, it is. Here, let me rewrite these so we can read them. There's three sequences here, and they want to know which ones are linear and which ones are exponential. Exponential are going to be the ones that are geometric sequences. Linear are going to be the ones that are arithmetic sequences.
Yeah.
So let's talk about the top row. Is that linear or exponential?
The bottom row?
Top row.
That is
Top row on my sheet. That sheet right there. Is the top row linear or exponential?
exponential.
Okay. Because there's a multiplier between each term, a common one.
Yes.
Middle row, linear or exponential?
Linear.
Because there's a common number added to each term. And bottom row.
Exponential.
No, what's the difference? There's a 6 difference there, there's a 6 difference there, and there's a 6 difference there. So every term is created by merely adding 6 to the previous term. That makes it linear. In other words, it makes it arithmetic, and arithmetic are the ones that are linear, geometric are the ones that are exponential. In other words, up here, I get this term by multiplying the previous term by 4. Same thing with that. I got to multiply 12 by 4, and I got to multiply 48 by 4 to get that. But in the middle one, I got to add 1, I got to add 1, I got to add 1. And here I'm adding 6. All right. All right, let's look at number 6 here. This is the function they want us to talk about.
All right.
You need to know, before you can figure out the transformations, which is their first question, you need to know what the parent function is. What is, I'm going to call g of x the parent function.
All right.
What is it?
What is g of x?
What's the parent function? In other words, what you're looking at here is not the parent function. That is the transformed function.
Yeah.
So you have to figure out what is the parent function in this particular case. It's 2 to the x. Okay. And the graph of 2 to the x, as long as we're doing it, looks like this. Almost all exponential functions look like that.
Yeah.
Okay, so that's what that function is. Now, how does f of x differ from this? There's 2 things that are going on. There's 2 transformations. List them.
Yeah.
What's the first one?
There's a stretch of 3.
A vertical stretch.
Vertical stretch 3.
Because you can have horizontal stretches also.
Yeah.
So you have to specify whether it's vertical or horizontal. What else is happening?
There's a vertical shift down 1.
Down 1. Yeah. Perfect. That's exactly the way you want to answer A.
Yeah.
Okay. Write the equation for the horizontal asymptote. Well, first of all, let's look at our parent function. There is a horizontal asymptote that is the x-axis. In other words, our parent function is never going to touch the x-axis. As it goes to negative infinity, it's going to get closer and closer and closer, but it's not going to touch it. That's kind of the definition of horizontal asymptote. Now, what happens to our horizontal asymptote when I make this vertical shift? It goes down by 1.
Yeah.
There's the new horizontal asymptote.
Yeah.
And the new graph is going to now kind of look like this. Okay? Based on the -1.
Yeah.
Now I still have to apply the 3, which is a vertical stretch. In other words, we've answered A and B. Oh, incidentally, what is the equation of that bottom red line? Because that's what they ask. Write the equation for the horizontal asymptote.
The new one or the first one?
The new one.
Should that be
It's at -1.
Yeah.
Because it was shifted down 1 from the original one, which was on the x-axis. What's the equation of a horizontal line look like?
Just y
Equals whatever the number that it's going through is. That bottom red line is going through this point -1 on the y-axis. And no matter where you're at on the red line, even if I'm over here, it's still y equals -1. If I'm over here, it's still y equal -1. So the equation of a horizontal line is y equals some number. The original horizontal asymptote was y equals 0. So horizontal asymptotes get moved by vertical shifts, not by horizontal shifts. If you had a horizontal shift, it wouldn't affect it. And the vertical stretch does not affect the horizontal asymptote. But the vertical shifts do. And now finally it says graph our function. Well, our function is the bottom black only vertically stretched by a factor of 3. And what that vertical stretch looks like is something like that. In other words, it tends to horizontally compress it.
Yeah.
That's what a vertical stretch typically will do. What it basically means is that every point that was on this curve, instead of being this distance away, it's this distance away, 3 times further. So you end up with a blue line there. All right. Now, I don't know if that's all they wanted when they asked you to graph the function.
I'm pretty sure it is.
Because we didn't put any points on that.
Yeah, they didn't have
Okay. In other words, we didn't find the X-intercept and we didn't find the Y-intercept.
Yeah.
And if I was asking somebody to graph it, I'd probably want both of those. But if they didn't ask for it, let's go on. Okay, so here they're giving you the parent function.
Yeah.
That's a parent function. And what would it be if you were to vertically move it 4 units down and vertically stretch by a factor of 3? How would it, what new equation would you come up with?
Square root of 2x.
Hold on. Where are you getting the square root?
You just have parentheses. 2x.
First of all, let's handle the vertical stretch first.
Alright.
Because I like working from left to right.
Alright, there's 3 parentheses.
Okay, so that 3 is multiplying the 2 to the x like that.
Yeah.
Okay, it's outside the function because it's a vertical transformation.
Yeah.
It's not inside. I don't have parentheses around the 3 and the 2, so the x is not acting on the 3. The 3 is strictly a vertical stretch factor. And now how do I get it shifted down by 4?
Near parentheses and 2x.
I didn't hear what you said, but I heard the word parentheses. We don't need parentheses. All we need is that.
Oh, yeah, it's a vertical line, yeah.
In other words, it's pretty much the same as the previous problem, only instead of moving down by 1, we're moving down by 4. In fact, I am shocked that they made the problems so similar.
Yeah.
All right. So here's our parent function. Again, they're giving it to us, and in this case, it's x squared.
Yeah.
And if it was changed, I don't want to call it f of x, because it's not. It's now g of x. But now I'm going to do all of these transformations to it. And they want you to list the transformations. So when you're talking transformations, you always list any reflections first.
Yeah.
And you always apply reflections first when you're graphing them. If you apply them out of order, it can affect the way the graph looks. So that's actually pretty important, the priority that you apply your transformations. The only ones that truly matter are do all reflections first, everything else in any order you like.
All right.
Now, in this case, let's just work left to right. What is the consequence of that negative sign?
It's a reflection.
Over which axis?
The x.
Because you can also reflect over y.
Yeah.
Second, what's the 2/3 do?
That's a shrink.
Vertical or horizontal?
Vertical.
Vertical shrink, because it's a number less than 1.
Yeah.
Third, what's the +3 do?
Horizontal shift left.
It's a horizontal shift, but it's to the right. Oh, no, my problem. My bad. Left 3. Okay. And finally, the last thing is what?
Horizontal. No, vertical shift down 2.
Right. Perfect. And once you get the hang of these, they're all that easy, really. I mean, there's a couple that we didn't do yet. We didn't look at, I'm going to graph the function of the only other 2 things you can do. Okay, one would be, no, we had a reflection over the x. If I wanted a reflection over the y, that would do it. Notice the difference. A reflection over the y-axis is a horizontal reflection. And all horizontal stuff is inside the function. It's not outside. All your vertical stuff is outside the function. All your horizontal stuff is inside the function. And the other thing that we haven't done yet is if I put a number inside the function, what would that 2 be? This 2 right here.
That would be, I know this.
Is it vertical? First define whether it's vertical or horizontal.
It's vertical.
No, it's inside the function. Everything inside the function is horizontal.
Okay.
You see why I say it's inside the function?
Yeah.
It's inside the parentheses.
Yeah.
As opposed to a 2 outside the parentheses, that would be a vertical stretch. But this is a horizontal what?
Horizontal stretch.
Shrink. They go opposite one another.
Alright.
In other words, if the number is a vertical and it's greater than 1, it's a stretch. If it's a horizontal and it's greater than 1, it's a shrink. And notice that when I was doing the last equation and I moved that to something like that and I said it's like a horizontal shrink, well, notice that horizontal shrinks look just like vertical stretches. So the fact that a number greater than 1 would be a horizontal shrink makes perfect sense. That it would go opposite of what vertical stuff does.
Yeah.
All right, let's go on. I think we've talked about all 6 things that you can do to a function. So list the transformations in this function here. In fact, I'm tempted to go on because I think you know these pretty good. What's this minus?
It's a reflection on the x-axis.
What's this minus 2? What's that?
The minus 2 is a horizontal shift left 2.
To the right by 2.
Yeah, right.
To the right. Remember the standard is always x minus h.
Yeah.
And positive h's are to the right, as you would expect. Negative h's are to the left, as you would expect.
Yeah.
And what's the 4?
A vertical shift upward.
On we go. Factor by greatest common factor.
That would be x.
Start with the number part.
Alright.
Always start with the number. What's the greatest number that you can factor out of all 3 terms?
3.
Okay. Now let's look at the x. What's the greatest power of x you can factor out of all 3 terms?
X.
Good.
Yes.
Now, what's left in the parentheses is what you get if you divide each term by our greatest common factor.
Yeah.
So what's this first term?
It's just x cubed.
X squared.
Yeah, x squared.
Remember, you subtract exponents.
And then minus 2x.
Let me stop you for a minute. The best way to do math is to always be checking. And by that I mean the moment I wrote x squared there, in my mind, I'm multiplying this by this to make sure I get what I started with. And do I? Yes. 3x times x squared is 3x cubed. I'm not going to wait till I finish the problem to do that. I'm going to do it along the way. Okay, what's next?
Just 2x, minus 2x.
And finally?
Minus 4.
All right, and that's all they want, is just to factor it by greatest common factor. And in case you're wondering, that quadratic does not factor nicely, so that's why they didn't ask us to take it all the way down. Had that factored nicely, they would have said fully factor it. Then I would have had to, start playing around with factoring that quadratic. next problem is a factoring problem. And as I've probably said to you many times, you can never get too much practice factoring. It gives most people nightmares. But if you do it the way I've tried to teach you how to do it, it shouldn't. It's a simple 3, at most 4-step process. What's the first step? Split up the x's. That's step 1. What's the second step?
Find our signs.
Perfect. What are the both signs going to be? And you want to find both signs. What are they?
Plus.
No. If they were both plus, you would not produce that as a number. Remember what the fourth step is. Remember what factoring is. Factoring is the reverse of foiling.
Yeah.
Well, when you foil two terms together, the very last step produces this minus 30. And it involves multiplying that number times that number. So the only way you could get a minus is if my signs were opposite. One has to be plus, one has to be minus. And in this case, it doesn't matter whether I put plus minus or minus plus.
Yeah.
So that's step 2. If you do the first 2 steps right, the rest of it is relatively easy. I now want factors of 30 that subtract, because of that minus sign, to the coefficient in front of the middle term, which is 1.
Yeah.
So what factors of 30 subtract to the number 1?
30 and 1.
That subtracts to 29.
Oh, yeah.
Let me help you on factoring. You always start with that.
5.
Okay, but I still want to help you on factoring. The way I factor is to start there. Next thing is I try to figure out if I can cut that in half, and I can't. Since I can cut it in half, I got to double that. So 15 times 2 are also factors of 30. Now I can't cut 15 in half anymore, but I can cut it in thirds, which gives me a 5 there. I got to multiply this by 3 to get a 6, and now I'm done. I've found all the factors of the number 30. And these are the 2 that I was looking for. Now, that's 3 steps. There's one last step for this problem, and that's figuring out where to put the 5 and where to put the 6. What's the formula for doing it? What is the rationale for doing it, I should say? You put the larger factor.
So 5 versus 6.
No, the larger factor, which is 6, goes with the sign of the middle term. Sign of the middle term is plus. The 6 goes there.
Yeah.
5 goes there. That's how we factor elementary factoring. Almost all your factoring problems are going to be, this is as simple as they get, really. But as long as there's no coefficient in front of the x squared, this technique that I'm teaching you or have taught you is by far the simplest, easiest one to learn.
Yeah.
Even if they don't teach you this one. And most school systems do not. They'll teach you something called the California method or the diamond method or something extremely complex, confusing, and everybody hates. So when you're dealing with simple quadratics, just use this 3-step process. Or 4th step, if there's a minus sign in front of the number, then it's a 4th step, because you have to figure out which factor goes with which sign. All right. Use the following quadratic. Now, this is a quadratic that has been factored, first of all. And the only reason we know it's a quadratic is because if we started multiplying it back together again, we'd see we have an x squared term, an x term, and a number.
Yeah.
So that's why it's a quadratic. Now, identify the x-intercepts. In other words, it's some quadratic that looks like, I don't know, quadratics look like that, parabolas. But how do we figure out how to identify those points right there? Those are the x-intercepts. What's the y value at those points? What?
It's
There's the y-axis. There's the x-axis. At the 2 points that I've circled, what is the y-coordinate?
0.
Okay. So, to solve for my x-intercepts, I set y equal to 0. Y is the same as f of x. Okay? So now I've got this equation, which will tell me what my x-intercepts are. What are they? The only way two numbers can be equal to 0 when you multiply them together is if one of them is 0. Has to be. So what makes that 0?
They're both one's -2 and the other one's 4.
One's -2 and one is 4. Is that what you said?
Yeah.
Okay, that's your x-intercepts. And that's how you figure it out, is you let y be 0 because at the x-intercepts, that's what y is.
Yeah.
And then you solve the quadratic. And the way you always solve it is, well, normally you'd have to factor it. Normally they would give you a quadratic that had been multiplied together. And they would say, what are the x-intercepts? And you would have to first factor it. But after factoring it, now you can solve this equation. And it's not an easy equation to solve if you're in quadratic form. It isn't. You have to factor it in order to solve it. Identify the y-intercept. Well, it says put the quadratic in standard form. What that means is multiply it out, FOIL it. What is it if you FOIL it?
That way. Foiling it.
Multiply every term by every term. In other words, that times that, that times that, that times that, that times that. That'll put it in standard format. So do the first one. What's x times x?
X squared.
What's x times -4?
-4x.
Keep going. You've done the F and the O of FOIL. Now do the I and the L. I is the inside terms. L is the two numbers. Inside is the +2 times the x. Two x. And finally the L is +2 times -4. -8. And now, as with almost all of them, we can always combine those two middle terms. What do you get when you combine those two middle terms? Those are the only two terms that are like terms. They're both x's. What's -4x plus 2x?
It's just -2x.
-8. That is in standard form. Okay? In other words, the form they gave it to us in originally was actually X-Intercept form.
Yeah.
But this is standard form, where you have the full quadratic. And then finally, identify the Y-intercept. That's actually easier to do than the X-intercepts.
Yeah.
On the Y-intercept, what is X?
On the Y-intercept, what is X?
Uh-huh. What is X's value? In other words, we went through this before with the X-intercepts.
Yeah.
Well, yes, X is 0, right? Right there? Well, notice that when you plug in X of 0, that term goes away, and the only thing you're left with is that number, -8.
Yeah.
So Y-intercepts are almost always this number, that final constant.
All right.
And Y-intercepts are almost always easier to calculate than X-intercepts.
Yeah.
Just because of that thing. All right.
Yeah.
They want you to find the discriminant and tell me the type and the number of solutions to this equation. Now, first of all, the discriminant is what? What's the formula for it? It's the part that's under the radical sign. Uh-huh. The discriminant has to do with the quadratic formula. Okay? Quadratic formula is, do you have it memorized?
I did, and I forgot this past week during studying.
Well, rememorize it. It's not going to go away. And I mean that. You're going to be dealing with the quadratic formula for the rest of your math career. That's it. Now, the part that is under the radical sign is b squared minus 4ac.
Yeah.
Now, first of all, tell me what a, b, and c are for this particular quadratic.
A is 9, B is 12, C is 4.
Now, tell me what b squared minus 4ac is. The best way to do this is just to plug it in. Don't try to do the math at any point. Just plug in B, A, and C. In other words, this is what I'm suggesting you do it like this. I'm going to plug in 12 for B. I'm going to plug in 9 for A, and I'm going to plug in 4 for C. Now simplify. If you try to do all of those in one step, it's really easy to make mistakes. Well, 12 squared is 144, and 16 times 9 is also 144.
Yeah.
So the discriminant is equal to 0. And when your discriminant is equal to 0, there's 3 possible things the discriminant, and this is why it has its own name. The discriminant can be positive, and if it's positive, you have 2 real solutions. Yeah. If the discriminant is negative, you have no real solutions, but you have 2 imaginary solutions. And if the discriminant is exactly equal to 0, then you have exactly 1 real solution.
All right.
No imaginary numbers, just 1 real solution.
All right.
We get through this whole thing?
Oh, no, I only had to do the first page. Actually.
Oh, okay. Okay, good. Because, yeah, we didn't get all that far. Oh, nice. More statistics.
Yeah. Hooray, I guess.
No, I'm getting used to it now. I figured out a lot of what I didn't know just by the fact that everybody has been on statistics for so long. It's forced me to learn it.
Yeah.
All right, Nick. I will talk to you next Wednesday. Oh, when is your spring break?
Oh, I'm on spring break next week, the next Wednesday.
Is your mom's intention for you not to have any tutoring next week, you and Anna?
Yeah. I'll be on vacation.
Okay. I will go in and cancel your next week. So I will see you I'll see you 2 weeks from Wednesday.
Alrighty, sounds good.
And tell Anna the same thing. I'll cancel her next Tuesday night.
Alright.
All right?
Alright.
All right, Nick. Have a good vacation. Bye-bye.